Okay, we would like to prove the Steiner-Lehmus theorem, which says that if the internal angle bisectors like AE and CD are equal, then the triangle's isosceles. However, this is not such an easy task as has been proven over the last 100 or so years. So first, we want to establish two results that we call lemmas here. The lemma one will be this this first video. We have three videos lined up here. In the first video, we want to say that if we have a quadrilateral where these angles, angle 1 and angle 2, are equal or congruent, however you want to describe that equality, then these 4 points are on a circle. This is not the theorem that you might be used to. The one you might be used to is, given a circle, is the converse. Given a circle, you inscribe a quadrilateral in a circle, and of course, angle 1 is going to be congruent to angle 2 because they share an intercepted arc. So this is an obvious result, but the result we're looking for here is the converse. It's an existence theorem. We say that if this quadrilateral has this property, there exists a circle that contains all 4 of these vertices. So it's much different than the one we're used to. And so first off here, we know that 3 points determine a circle. And if we want to find the center of that circle, what we're going to do is we're going to bisect the chords that are between these points. We can bisect 2 chords. Bisect 2 chords, and the intersection of those 2 bisectors, perpendicular bisectors, is the center of the circle that contains these 3 points. However, there's no guarantee about this 4th point being on that circle. And so we need to establish that the point at vertex C is on the circle as well. We want to show that circle exists that contains all 4 points, all 4 vertices. So now we're going to do that by contradiction. You want to say, suppose C falls in the interior of the circle and not on the circle. Then we know that we can extend CD, extend D to C to F on the circle. Okay? And now we immediately get a contradiction, and the contradiction involves the exterior angle theorem. Angle 1 is congruent to angle 2, but angle 2 is greater than angle 3 since it's an exterior angle to triangle ECF. So 2 is greater than 3. But 3 and 3 and 1 share an arc. So 3 and 1 are congruent, but 1's congruent to 2, so that's a contradiction. 2 can't be greater than 3. And now we suppose that C is outside the circle. And when we see that C is outside the circle, what we're going to do is extend C is going to fall outside the circle. We're going to draw this segment here that connects the point where DC passes through the circle on the circle to E. Okay, so this is your point F here. We're going to draw EF. And we're going to get the same contradiction. Angle 3's got to be bigger than angle 2 because it's exterior to this triangle. But 1 and 2 are given to be congruent, and we know that 1 and 3 are also congruent because they share an intercepted arc in common. So this is another contradiction. We contradict here and contradict here. Another contradiction. So we eliminated the possibility that C's in the interior, that C's in the exterior or the outside. So C must be on the circle, and we proved that there is a circle that contains all 4 points. Now we want to move on to Lemma 2 in the next video.